Okay, I'm going to tap the screen now. So hopefully things will be lined up. Okay. So here's the problem that we're given. This is taken from Dr. Hunter's discrete math textbook, which I'll put a link to in the description so that I'm giving it appropriate credit. Problem 16 from section 1.5, I believe. And the question is, starts off by giving us a few definitions. So here's the first definition. We say that an integer n is alphic if n can be written as 4 times k plus 1, where k is some integer. And then we'll say that an integer is gamic if it can be written as 4 times some integer plus 3. So these definitions are going to be useful for us, along with, I'm going to add 2 definitions here for us to remember that an integer is called even if it can be written as 2 times k for some integer k. And that an integer is odd if it can be written as 2 times k plus 1 for some integer k. Okay, so we've got 4 different definitions here that we're going to be juggling. I'm going to try and keep them straight using color coding. And let's look at this first problem here. It says to show that 19 is a gamic number. Okay, so in order to show that 19 is gamic, what we have to do is look up at our definition and see, well, what does it mean for 19 to be gamic? It means that we can write it as 4 times some integer plus 3. And so, well, for part A, you would say, okay, well, if n is 19, my goal is to somehow show that 19 equals 4 times some integer k plus 3. And so think about it, scratch your head. And, well, just using some simple algebra, you can subtract 3 from both sides to get 16 equals 4 times k. Divide 4 from each side to get that 4 equals k. And so to show that 19 is gamic, all that you have to do is say, well, 19, that equals 4 times 4 plus 3. And in this case, the second 4 here is that number that we were calling k. And so that would show that 19 is in fact gamic. Okay, so now that we've shown 19 is gamic, let's move on to part B. Part B is a little bit more involved. We've got a proof here. We're supposed to suppose now that we've got an alphic number x and a gamic number y, and we're supposed to show that x plus y is even. So we've got 3 different definitions to juggle here, and something to be aware of is that we just care about it being for some integer k, for some integer k, for some integer k. And in particular, these might be different k's that we're working with. So we want to make sure that we're keeping all of our variables distinct. So to do that, I'm going to be using subscripts like k1, k2, and k3. All that it means is that it's some integer k that might not be the same one as the other ones. Okay. So the first thing that I like to do here is we're supposed to suppose that x is alphic and that y is gamic, and then prove that their sum is even. So I'm going to split this up into what we're given and what our goal is. So let me come down here and write our goal. And we're given that x is alphic. We're given that y is gamic. And our goal is to show that x plus y is even. Our goal is to show that x plus y is even. And right now these are just some words on the page. And so what I'm going to do is use our definitions here to translate this phrase x is alphic and the phrase y is gamic, along with the phrase x plus y is even, into some more symbolic and mathematical symbols. So what does it mean for x to be alphic? Well, we're just going to use that definition that we're given to say that x is alphic if it can be written as 4 times some integer k plus 1. So to do that, I will say x equals 4 times k1 plus 1. And here I'm just going to say where k1 is an integer. And what does it mean for y to be gamic? Well, again, we just use our definition up here to say y is gamic means, by definition, that y equals 4 times some integer, I'll call it k2 this time, plus 3. And again, I'll make the note where k2 is just some integer. Okay, so that's giving us a little bit of a better idea of what we've got to work with here. But now let's also translate this last thing, this goal. What does it mean for x plus y to be even? Well, by definition, again, using the definition that we've got of an even number here, that's the same thing as saying that x plus y can be written as 2 times some integer, we'll call it k3 this time. So again, where k3 is some integer. Okay, so I've got all of my givens, I've got my goal, and all of them have been translated from terminology into mathematical expressions. And now really the only thing that we can do is somehow try and figure out how to write x plus y as 2 times some integer. So this is where we're going to start by, I like to just create a chain of equalities here. So I'm just going to write, our goal is to get x plus y equals something that equals something else that equals something else, and a few more times maybe, until we get it as 2 times, I'm just going to write some integer. Okay, well, let's scroll on back up here to see what we've got. What do we know about x here? And what do we know about y? Well, up here we've already used the definition of alphic and gamic to rewrite x in this way here, and to rewrite y this way here. And so what I'm just going to do is substitute those in for this expression x plus y. And I'm going to write that as 4 times k1 plus 1, where that 4 times k1 plus 1 is just coming from that first expression up there where we wrote x, and then rewriting y as 4 times k2 plus 3, where again I'm just pulling that straight from what we've already identified y to be. And now what we really want to do somehow is rewrite that expression as 2 times some integer. Okay, that's our goal down here. So can you figure out a way to rearrange terms, use some algebra to restructure this so that it's 2 times some integer? Go ahead and take a second here to try and figure that out. So pause the video and see if you can manipulate things algebraically to get it as 2 times some integer. And once you've done that, I'm going to go ahead and zoom in here and show you my method. First thing that I want to see is that we can combine some terms. Okay, we've got this 1 here and this 3 here. So I'm just going to add those together to give us 4 times k1 plus 4 times k2 plus 4. And I'd like to get it to be 2 times some integer. So what I'm just going to do is I'm going to notice, first of all, that we've got a 4 here, a 4 here, and a 4 here. And that means I could factor out a 4 if I want. But even better, I'm just going to factor out a 2 to give me 2 times 2k1 plus 2k2 plus 2. And all that's left is to make sure that the thing inside of the parentheses here is an integer. And since we've just got some integer here, plus some integer here, plus a third integer here, which means that, yeah, actually this whole thing inside there, that's just some integer. So if I wanted to, I could call that whole expression k3, and that would end up giving me exactly what I want up there. I would have written x plus y as 2 times some integer, which concludes the proof. So there's the entire screen. Hopefully you're able to see at least the kind of the layout of how things flow. Now, a proof that was well written up would skip a bunch of the steps that I did. It might start by saying define k3 to be this expression here, and then show that you can actually write x plus y as 2 times k3 to get it exactly in the form that we specified as our goal. But this should be sufficient. As long as you're showing that x plus y is an even number, then you're good. Okay, so I'm gonna go ahead and wrap up that proof and go on to part C. And C says to use a proof by contraposition. Now this is the part that I'm going to have you try and do on your own, okay? So I'm going to get you started, and to get started I'm going to erase everything that I've done here. And I'm going to leave up our definitions though. We're supposed to prove by contraposition that if x is not odd, so here I'm going to use our colors again. If x is not odd, then x is not alphic. And so here we've got an expression that looks like not p of x implies, trying to use color coding, implies not, I'm going to say a of x, where in this case p of x stands for x being odd, and a of x stands for x being alphic. And what a proof by contraposition does is it says, well, let's negate each of these terms and swap the order. So I'm going to rewrite this using the equivalence that we have by contraposition to say, well, I can rewrite that as not a of x implies not p of x. And that simplifies using a few, using double negation to give me a of x implies p of x. And so now we get to use exactly the definitions that we've been working with before. And I'm going to show if x is alphic, then x is odd. So go ahead and pause the video here. Well, actually, the video is going to end here. Your goal is to do part C on your own. So again, I'd suggest starting by writing out what you've been given, writing out what your goal is, and then seeing if you can come up with a way to use the definitions and algebra to get from your givens to your goal.